Thank you for inviting me. So the first thing I want to do is mention my co-authors on this project are Stephen Holland, he's down the road at UNCG, Aaron Manser's at Dartmouth, and Nicholas Muller, who's now at CMU. I have the wrong label for him. So there's a picture of me in my electric car. It's a picture of me anyway, and that's not my electric car. That's at the Tesla store. All right, a little bit of history about electric cars. Things have been pretty quiet in the market for electric cars for the last, 100 years or so. But actually, around 1900, electric vehicles actually had a pretty significant market share. About 30% of all cars sold in 1904 were electric vehicles. That's about 3,000 cars, so the market wasn't very big. And then from about 1930, let's say, to 1990, electric vehicles had zero market share. They just didn't exist. And recently, there's been a modern revival with cars like the Tesla, but also the Nissan Leaf and the Chevy Volt. So some quick summary statistics of where the market stands right now. This is from, loosely speaking, the summer of 2018. The United States, about 2% of the new cars sold have plugs in some manner. Right? It's a little higher in UK, a little lower in Germany and France. Pretty remarkable in Norway. It's a 55% market share. And as you can see, in all these places, these vehicles are very heavily subsidized. Right? So it's $7,500 federal subsidy for purchase of an electric vehicle, and some states supplement that significantly, as we'll talk about in a little bit. So this data now is a little older. To get vehicle registration, you have to buy it, so we're not, we can't buy it every year. So we bought it for a project a couple years ago. So in 2014, the darker the blue in this picture, the more electric vehicles are registered in a given county. And you can see there's a lot in the West Coast, but it's not purely just a California phenomenon or anything like that. They're pretty widely distributed throughout the United States. Again, this is from the same time period. These were the cars that were being sold. These are pure electric vehicles, so we have things like the Chevy Spark, Fiat 500, Ford Focus. Those are just the pure electric version of existing gas cars. They just put an electric drivetrain in there. Then you have dedicated electric vehicles like the Nissan Leaf and the Tesla S. Again, these numbers are old, but you can see that most of the action here is with the Nissan Leaf and the Tesla S. And it really continues to be the case that a large majority of vehicles sold, electric vehicles sold, come from Tesla. All right, so today what do I want to do? Two main points. First thing I want to look at is what's the environmental benefit of an electric vehicle relative to a gasoline vehicle? And then I want to point out this phenomenon we discovered in the course of this project, which we call pollution export. I'll give you more details about what that entails as we go along. All right, so what's the environmental benefit of an electric vehicle? How do we define this? Well, suppose we have a person that's about to buy an electric car. They walk into the dealership, and they're about to buy a car. They walk into the dealership, and they're thinking, should I buy an electric car or should I buy a gas car? All right, we want to think about the consequences of that decision for the environment. So if they buy the gas car, they're going to generate some air pollution. We'll talk about that, how we calculate that. And if they buy an electric car, they're going to generate some air pollution from the electricity that's used to charge the car. So what we want to do is just compare those two numbers, right, and see which one's bigger. All right? If the electric vehicle produces less air pollution than the gasoline vehicle, then that's the environmental benefit, is the difference between those two numbers. Right? And so if you were a concerned citizen, you kind of want to know, is this electric car good for the environment or not? You'd probably do a Google search. And if you do that, you would turn up some stuff, probably by the EPA or maybe the Union of Concerned Scientists. And most likely that information would be about the carbon dioxide emissions of an electric car versus a gasoline car. All right? And so that's interesting, and we will talk about the carbon dioxide emissions as part of the emissions from these cars. But it's not the whole story. Right? So generally speaking, and this is consistent with our results as well, there's a slight advantage if you only care about carbon emissions to having an electric car versus a gasoline car. Right? But what we do in our study is that we focus on these other pollutants, these things called local pollutants. Right? Carbon dioxide is a global pollutant, generally affects everywhere in the world the same way. Or a local pollutant, it really matters where that pollution gets emitted, as we'll see. And so these are pollutants like sulfur dioxide, nitrous oxide, particulate matter, and volatile organic compounds. Right? And so what we're going to see here is it really makes a difference where the car is driven, how severe these pollutants are. Right? And so it can be important because it can reverse the sign. Right? So if you just cared about carbon, say electric vehicles on average are a little bit better than gasoline vehicles, but we can reverse that, and as we'll see, we can reverse that significantly if we start worrying about some of these other pollutants, right? These local pollutants. So we'll just jump to the main results. This is the, one of the main figures from the paper that we wrote about this topic. It may be a little hard in the back to see. Can you distinguish the colors in the back of the room? Okay. So green is places in which an electric vehicle, accounting for both global pollutants, CO2, and local pollutants that I listed, has a positive environmental benefit. That means if you're in that store and you end up buying an electric car, you generate a benefit to society from reduced air pollution emissions. All right? And as you can see, most of those green places are in the West. Okay? The other colors, the red and the oranges, are places where the gasoline vehicle has less air pollution than the electric vehicle. So if you purchase the electric vehicle, you're actually making air pollution worse, right, than the gas vehicle you would have bought. Right? So these calculations are done for a particular electric and gas car comparison. We can consider a bunch of different comparisons, but this is for the Ford Focus. Okay, so we take the Ford Focus because it has both a gas and electric version. So we're comparing two very similar cars. A couple numbers at the bottom of the screen. So in Los Angeles, over the lifetime of the car, we can talk about how we modeled that, assumed 150,000 miles driven, 10-year lifetime. The electric vehicle generates about a $5,000 benefit. Okay? In Fargo, North Dakota, the electric vehicle generates about a negative $5,000 benefit. Okay, so society's $5,000 worse off because you bought the electric car rather than the gas car in Fargo, North Dakota. In New York, it's a bit of a wash. Okay, we have a number, $32, but that's basically trivial. Okay. All right, so why do we, yeah, sure. Yeah, that's okay. In economics, it's like I wouldn't have gotten this far, right? People go after you for your title in economics. So.
What is considered to be the benefit of reduced CO2?
So
Do you have a measurement of temperature reduction?
Yeah, so let me go back here. So for these guys, SO2, NOx, PM, and VOC, I'll show you exactly what we do for that. Okay. For the value of a carbon emission, we completely punt and just use the EPA SO2. I mean the EPA social cost of carbon. Right? So, and we have a very good reason for that, right? In that we understand how to value these things. I do not want to make a career of trying to understand how to value that.
Yeah.
Right? So what do we use? Well, we use a number that's out there. Okay? And we can talk, I don't want to talk about that as part of the main talk. I can talk to you after you want about the issues with that. But like I said, I do not want to get into I don't want to get into making that part of my career to determine what the social cost of carbon is. Okay, so we were going the wrong direction on the buttons. I'm having a nice tour of my slides. Good, okay, so why do we get such differences across different places in the United States? Well, we argue that local factors make a big difference when you're talking about local pollution. Right, so Los Angeles has a very large population, so when you drive your gasoline car in Los Angeles, you're affecting a number of people. Right, it's kind of a unique airshed as well because the mountains ring the Los Angeles area and the pollution tends to get stuck in that area. And also, as we'll see, the Western electricity grid is fairly clean. I don't think there's a single coal-powered power plant in the state of California. Now, they get some electricity from other states, but I think that's pretty much true. Fargo, North Dakota was kind of the opposite. When you drive your gasoline car in Fargo, North Dakota, you don't hurt anyone because nobody lives there, right? On the other hand, when you plug in your electric car, it's powered predominantly by coal. Okay, so it makes sense that that generates a lot of pollution damage, not just in Fargo, North Dakota, right, but in many other places, the way the grid is dispersed, and the emissions get dispersed from smokestacks. New York is a wash. It's a large population, but the grid's fairly dirty in the east as well. All right, so I would like to get into some details about how we generate these numbers. And to do that, we go through a three-step process. We need a model of the electricity grid. We need a model for air pollution, right? So when you emit air pollution from a smokestack or a tailpipe, where does that pollution go and who does it hurt, right? Again, with carbon, you don't need to worry about that, right? But with these local pollutants, that's going to be a very important part of the story. All right, and then we gather some data from the Environmental Protection Agency on various regulations they have in place about smokestacks and tailpipes. And miles per gallon and things like that. So here's the electricity regions. Each color is a different region. I have to talk a little bit about the minutiae of the electricity grid. But the basic idea that we have in this paper is if you plug in your car in any of those colored, let's say green colored counties, we get the same response from the grid, right? So you plug in your car, some power plant, you get a little extra demand for electricity, so the grid has to balance that, and they have to increase production at some power plant. Maybe they decrease at some other power plant, right? But what we're saying is anywhere in that green area, the response from the grid is the same. But that doesn't mean the pollution response is limited to that green area, because you might have to change production in some power plant fairly far away from where the car was plugged in. And furthermore, the stuff that comes out of the smokestack from that power plant may drift hundreds of miles, right? So the response is the same for a given color, but that response is not limited to the colors, right? And that's an important point. That's going to come into the pollution export we're going to talk about in a little bit, okay? But that's a rough picture of the electricity grid, broken up into 9 different components. Okay, and so once we've done that, we need to think about, right, if you plug in your electric car, so we're economists, we're always thinking about marginal this and marginal that. And in this case, the marginal thing that we're looking at is plugging in an electric car in a county bumps up electricity consumption by a little bit, right? And so what does that do? That's going to increase emissions of pollution a little bit, all right? And so we have data from all power plants in the country, and these power plants have monitors on them, so we know exactly how much pollution comes up out of those smokestacks every hour. And so we can do an experiment, right? What hour are you going to charge your car? We have a little increase in pollution. We have a statistical relationship between the total amount of electricity in the system, the electricity load, and pollution. So I'm just showing you a graphical interpretation of that here. And basically, we just determine the slope of that relationship, right? So if your electricity demand goes up a little bit, emissions go up by a little bit, right? And that's what we're thinking about as the pollution response from plugging in an electric car in one of those green areas, well, one of those colored areas that we talked about on the previous slide. Okay, then once we have an idea what comes out of the smokestacks, right? As I said, we need to know where that pollution goes and who it hurts, right? And so this is a fairly complicated modeling process, and one of the co-authors on this paper has essentially dedicated his career to making a model of this process, right? And so we have pollution coming out of a smokestack, right? Then, as I'll put some chemistry up on the board in just a second, but what happens is that pollution through chemical and physical processes gets dispersed. Okay, people breathe in that pollution. That's what we call ambient concentrations. That's the amount of particulate matter that's in the atmosphere around Raleigh today, right? That's an ambient concentration of pollution. People breathe that in, leads to health consequences, right? And then we value those health consequences, premature death and other sorts of things like that. And so we take into account, a lot of things. How high is the smokestack? Ironically, they keep making electric power plant smokestacks higher and higher, which actually disperses the pollution over a greater area. We look at which way the winds blow, right, because that's going to have an effect on where that pollution is going to go. We look at human health and ecological damage, right? So you have acid rain, you have heart and lung ailments from breathing in particulate matter and things like that. And then how do you value that? Well, we have epidemiological studies that say, if pollution goes up a little bit, more people die, and then how long would they have lived, and what's the value of their life? We add all that up together to come up with a measure of the harm associated with an additional unit of emissions from every power plant in the country. Okay, so that's what we're capturing. And the harm is measured at the county level. So you saw that map already. We're going to just say, all right, if you emit a ton of nitrous oxides from this power plant, it affects this 20 counties, right? And this is the effect, so sum of all the damages, accounting for human health and other ecological effects of pollution. Building degradation, you see buildings turn black. Have you seen that in a city, right? Over time, buildings get darker and darker. And you come and you power wash it, and it looks real nice for a while, right? That's included. The effect on human health is by far the dominant effect here. Okay, much more important than any of the ecological values or the damages to buildings and things like that. All right, so as promised, a little bit of chemistry and physics. Now, I've forgotten all the chemistry and physics I learned in high school, so I made up this notation. So if there's anybody that has any knowledge of chemistry and physics in the audience, please don't say anything. But the basic idea here is some of the stuff that comes out of smokestacks in and of itself isn't so harmful. And that's particularly true for something called nitrous oxides, NOx. But it combines with other things in the atmosphere, in particular ambient ammonia, to form particulate matter, which is the stuff that you breathe in, and that's the stuff that's really harmful. Okay? So SO2 also causes, that's what leads to acid rain. But nitrous oxides and these volatile organic compounds also combine to form ozone, right? And so the basic idea of this slide is that the stuff comes out of the tailpipes and the smokestacks, it forms smog, and smog is harmful. Okay? And this is some of the little bit of the chemistry that's underlying what's happening there when smog is formed. Right? As far as the physics go, essentially we assume there's a Gaussian plume. You take a normal distribution, spin it around the central point, right? You're going to get some kind of a diffusion over two-dimensional space. And maybe the winds blow it a little bit, so it's kind of a deformed distribution. Right? But you can think about that as for where the pollution goes. And then it has these chemical processes, and then we get damages. And as I said, human health is by far the biggest damages. Economists identify something called a value of statistical life, and that's how we're valuing the mortality. So when somebody dies, and what does society lose when somebody dies? Okay? And we're assuming that's positive, that society does lose something when somebody dies. Okay, and like I said, we also have building and material degradation and visibility and recreation changes, but it's really human health that's driving this. The number, the value of statistical life, which for this study, I think we're using about $6 million per life, is really what's going to drive the damages. All right, and then finally, as I mentioned, we do get some data from EPA regulations. Again, if you do a web search, you want to know some characteristics of cars. This is a gas Ford Focus. Tells it how many miles per gallon it gets, so we know how much carbon dioxide it emits into the atmosphere. It also has some information about, I think it's a little hard to read, but the smog rating. And so we need a little more detailed information than that, but that gives you an idea of some of these other things that are coming out of the tailpipe, right? Not just carbon dioxide. And they have the same information now if you have an electric car. They tell you approximately how much electricity it uses per 100 miles or per mile, right? And so we make some assumptions about how long the cars are driven. And that tells us, how many kilowatt hours of electricity they require. That other chart I showed you a couple minutes ago says if you want to produce that 100 kilowatt hours of electricity, it's going to produce this much pollution. Right? So that's how we do the calculations for the electric car and the gas car.
Could you touch on something we never hear about? How much healthier the air is today than it was?
I'm going to have a great slide to show you that in just a minute. Thanks for teeing that one up for me. Right? So that's coming real soon. Right? Okay. So. A number of caveats to this analysis. The calculations that we do focus exclusively on the damages from driving the car, right? So each car, we assume, is driven about 150,000 miles over a 10-year lifetime. We don't look at what's called life cycle analysis, or I call it here upstream pollution and even downstream pollution. We only consider driving the car. We don't consider any pollution that might be created by manufacturing the car, mining the coal, drilling for the gas, transporting that to the power plants, refining the gasoline, or anything like that, right? We're just looking at driving the car. And likewise, I don't have it on the slide, but we don't look at any disposal costs, right? We don't think about what happens to the batteries after the electric car is no longer used, right? And then any sort of costs associated with landfilling and various things that you throw away when the car dies. It's kind of embarrassing at this point. These numbers that I showed you are from the electricity grid in 2010 to 2012. Study came out a year and a half ago. We started working on it 3 years before that. And to do that, you need to get the latest emissions data from the EPA, and it takes a couple years for them to do that. So that takes us all the way back to 2010, 2012. We are working on updating this with newer information. As almost everybody knows probably here, there's been some really massive changes in the electricity industry due to fracking. So natural gas has become much cheaper. It's displacing coal production. We might expect that has made electricity cleaner. Right? So I'll show you some brief evidence on that in a little bit. We're currently working on that to do the same type of study that we did here, but with the updated information about what's happening to the electricity grid. Gas cars could potentially be getting cleaner as well over time. Right? And then directly to your point, so what I did here was I took the model that we just described. And I said, OK, let's do the following experiment. Let's take 1974 vintage vehicles. All right, we can go back and we can see how many miles per gallon did a typical 74 car get, how many grams of those other pollutants did it emit per mile. And let's suppose that we have today's fleet of cars driven in today's places, but they were all 1974 cars, polluting like 1974 cars. Right? What would the total damage be due to air pollution, evaluated by the exact same methodology I just explained? Okay? And so maybe you can see those numbers, but it turns out there'd be about $180 billion worth of damages per year if we had 1974 cars driving around, gasoline cars. Okay? And you can see the graph over time. 2010, maybe I can even use a clicker, we're down to about $40 or $50 billion per year. Right? And you can also see sort of where we started to make progress. There's obviously a lot of changes around this time period in the late 70s, right, and then some other periods in the 80s. And things have been pretty flat over the last decade. Okay, there's been very marginal improvements in miles per gallon. And we're at the point with tailpipe emissions where you get more particulate matter from your tires and brakes than you do from the tailpipe. Okay, so you know, and you can just think of this as an exponential decline, right? Eventually, at some point, it gets harder and harder to push on this dimension, right? So you can see we've made fairly dramatic improvements by our measures of air pollution damages over the last 3 or 4 decades. Okay, so that's the electric side. On the gas side. On the electric side, this is a graph of power plant emissions, so normalized so that in the year 2010, they're all equal to 100, from 4 pollutants, SO2, NOx, PM, and carbon dioxide. And this is over the last 7 years. So compared to 2010, in 2017, we're emitting 75% less sulfur dioxide, right, in a 7-year period, which is remarkable. I don't have another slide that shows you how it changed, you know, going back further, but this is sort of an unprecedented period of change in the electric power sector. Okay, so emissions have gone down significantly. Some of the other ones, even carbon dioxide emissions are down 20% from 2010 levels, right? So it's a pretty remarkable change. Now that suggests that electric vehicles are going to do a little better now, just 7 years later, than the data I showed you earlier, right? But we have to be careful because what we are estimating is marginal emissions, right? And this is total emissions, and there might be a difference between that, right? In fact, we are finding a difference between that. That marginal emissions are not going down as fast as total emissions, right? In fact, you can imagine a situation in which we have tons of renewable energy coming onto the electricity grid, and they use that whenever they can, right? But the stuff that they actually dispatch could still be fairly dirty, right? And so in that case, when you demand a little extra electricity, it's actually coming from a coal plant, not from those renewable resources, because they can't, what's called in the electricity industry, they can't dispatch it. They just take it when they get it, right? And so if you're charging your electric car at some other time, it could be from fairly dirty electricity, okay? But the grid is getting cleaner remarkably fast, and it does actually have an effect. In the East Coast, electric cars are getting a little bit better. We don't have the numbers yet, and I don't want to be quoted on those because we're still working on it. But it has been kind of a remarkable period. Okay, so next thing, pollution export. As we've talked about, when you drive your car, or in gas or electric, in a given county, the consequences of that driving does not just stay within that county, right? You might affect people farther away, right? Because the pollution might get dispersed into other places. What we've discovered, and it makes sense, but we didn't really think about it before we did the study, is that electric vehicles export pollution to other states. All right, now let me show you that graphically. So here is a Ford Focus gas car driven in Fulton County, Georgia. All right, so the dark colors show higher concentration of pollution. And so as you can see, almost all of that pollution is highly concentrated in 3 or 4 counties or 5 or 6 counties around where that car is driven. Right? It makes sense. Tailpipe emissions come out at 2 feet, right? So they're very low, and they tend to stick around and harm people right near where the car is driven. Okay? So what we want to do now is the exact same experiment, but we want to plug in that car into the electricity grid instead. Right? So here I always pause for dramatic emphasis. This is the gas car. This is the electric car. Okay? So what has happened is you plug that car in, the whole grid, the whole East Coast grid reacts to that change in demand for electricity. Right? Those power plants have very high smokestacks, it disperses the pollution. And you can see that Atlanta is green. Right? So Atlanta doesn't really suffer the consequences of the pollution from that car, whereas most of that ends up in the Charlotte area in this picture. Okay? But it also has far-reaching consequences throughout the eastern United States. All right, so here's another way to visualize that. The picture on the left is the state version of the picture I showed you earlier, right? So we're just aggregating up to the states. And again, green is good. Electric vehicles generate environmental benefit in the West, right? They generate a negative environmental benefit in the East. Right? That's the same picture we saw before. The picture on the right says, well, what if, from the state's perspective, we only care about the pollution that ends up in the state in which the car is driven? Okay, so if I'm from North Carolina, right, I might not care if some of that pollution goes to Virginia, right? And so now you can see that electric vehicles are a pretty good deal for the environment just about everywhere, right? Because they export their pollution to other places. All right, so somebody asked me about public choice before the talk today, a little bit on that here. States also offer subsidies for purchasing an electric vehicle. This changes over time, again, to be consistent with the earlier data I presented in the time period of the study. We can look at the subsidies that were offered in 2014. You can see some of these are pretty substantial. Colorado and Georgia in particular had very generous subsidies. Right? And so there's all kinds of other benefits. There's carpool benefits, parking benefits. Even some places have reduced electricity prices for people with electric vehicles. But the important point is these subsidies are more highly correlated with the picture on the right than they are with the picture on the left, right? And so that's just a simple insight. If you're a state politician, what do you care more about, the picture on the right or the picture on the left, right? You care about the picture, am I doing that right? On your right, yes, okay? Because that's the harm to the constituents in your state. All right, so yeah, pollution, so I think this is the point I want to make, that when you drive your electric car in most states, you're making society worse off, but you're making your state better off. That's kind of the bottom line, because you're sending the pollution somewhere else. Okay. All right, so those are my conclusions, right? It really depends. Yeah, well, go ahead. Let me make my conclusions, and then I'll get your question, right? So is there an environmental benefit for an electric vehicle? It really depends. It really depends on how clean the grid is, right? The Western grid is pretty clean, right? They don't have coal plants, they have hydro. Okay, there's been a lot of changes in the electricity grid just over the last 6 years, so that's going to make electric cars look a little bit better, right? But they have a long way to go in places like Fargo, North Dakota, right, before they generate an environmental benefit. The second point is that they export pollution to other places. Okay, so that's my summary, and if you want to ask some questions, I'll be glad. We have some time.
So would the pollution export phenomena insinuate that in terms of human health, electric cars have a comparative advantage in urban areas?
Yeah.
Since the pollution can be exported from these densely populated urban areas to less human populated rural areas?
Yeah, but it turns out, I mean, we're accounting for that, right? So it turns out that, like if you drive it in Atlanta, the whole East Coast gets affected, right? So there's other urban areas that are being affected by it, right? So we're accounting for that when we do these calculations. But you're right, it does tend to distribute it outside of urban areas, right? But it still could make society worse off, even though it's doing that.
But there might be there could potentially be a control mechanism by which, if you're utilizing electric cars in specific regions, and then you can account for like winds and whatnot, that it could have a less per capita negative impact on human health than if you're using gas cars in that region.
Yeah, you could try to find the best place, I suppose, and Los Angeles is the best place, right? Because when you drive your gas car, you hurt just tremendous amounts of people, right? And you disperse the pollution to fairly uninhabited places with a relatively clean electricity grid. So that's the key thing. You have to consider the electricity grid and where it's going and who it's affecting, right? Okay. So yeah, it generally seems like a good idea. We should get it out of the urban areas, but it depends on which urban area we're talking about, right? So when you get it out of Atlanta, it makes the country worse off.
I'm probably just being obtuse, so help me understand. I'm missing a step in the comparison of whether you're better or worse off in a county or a state versus the others. With CO2 emissions...
It doesn't matter. It doesn't matter, absolutely. That's right. That's right. That's right. Right, so when we look at the difference between what we called full damages and native damages, local damages, we just looked at local pollution. That's right. I should have mentioned that. Thanks for catching that. That's right. Because you're absolutely right. Carbon is uniform. It doesn't matter. But these other pollutants are really important, is what we're saying. And for those, it does matter where the pollution goes. Absolutely. Thank you for the correction. Yeah.
So how many vehicles are you using in your scenarios of electric on the grid? Because at some point...
Good question. Excellent question. So, right.
California especially.
That's right. So everywhere that we look at, we use the same procedure. What's the extra emissions from a kilowatt hour of electricity demand? Okay. Now, you might start to think, if we get enough electric cars, then you might want to do some other kind of calculation. In particular, if you learn a little math, instead of just the extra change, you might want to integral over the whole curve. But the argument that we make in the paper is that if the grid was, if the total fleet of electric vehicles, not the sales, but the total fleet was 5 or 10% of the total, if electric vehicles made up 5 or 10% of the total fleet of vehicles, not sales, but the fleet, then the extra electricity demand would be in sort of the normal variation in demand for electricity. Okay? So there's a large range, we think, of electric vehicles for which the calculation that we did is the appropriate one. Okay?
So if you go above 5%.
Yeah, now that's the stock. That's the stock of vehicles, not the sales, right? Right. So that's a lot of electric vehicles. So that would be, there's 300 million electric vehicles, so 10% would be 30 million, right? And so there's maybe a million on the road right now.
But at what point in time do you need additional power plants?
Well, so again, that gives us a rough idea, right? We sort of can handle that kind of, 5 or 10% influx within the normal, variation of the power demand. After we get past that point, that's the stock of vehicles, right? Then we really start thinking about extra power plants. That's right. Yeah. So we're not doing that in this study at all.
Just a question. Your statistics are based on coal-fired energy. What happens if we move toward nuclear energy? Would that make
So, sure, because, yeah, well, I want to be careful there. So we're using the current electricity mix, which involves some nuclear power, right? And so then it's a question of when that's dispatched and when the coal plants are dispatched. And we're accounting for all that. The real tricky part with nuclear power, of course, is evaluating the environmental harm from the risk of nuclear waste. Right? And that's another one of those things that I wouldn't want to make my career trying to evaluate that number. Right? Over the course of our study, and the data I showed you about what's happening in the electricity grid over the last 10 years, nuclear production is essentially flat. Right? And I think they just stopped producing, construction of 2 nuclear plants in South Carolina. So I'm not sure, the U.S. is going to have a big, but yes, nuclear power would get rid of carbon emissions and would get rid of local pollution, and you're left with nuclear waste. Is that a worthwhile trade-off? That's not the question I'm going to answer. That's a great question, but that's not the question I'm going to answer, right?
Could you go back to the money, because it's interesting. You get all these incentives to change your behavior, to buy electric car. I'm wondering what the total cost is to the feds and the states, and do they really get their money's worth?
Do they get their money's worth? That's right.
$4,000?
Right. So the argument I've showed you today would be no, right? Even in Los Angeles, you're only getting $4,500 worth of benefit. We have to be, again, careful with that. This wasn't on my list of caveats, but it should have been. So people would tell a dynamic story, right? That electric cars are expensive right now, that the more you produce, the cheaper they get, and therefore that's why we need to have the subsidies, so there's an additional component. They may also say that we spend money, worrying about wars in the Middle East, and if we all go to electric cars, we won't have to spend that money. That's another calculation that I don't want to make, is what the value of reduced expenditures on defense would be if we all went to electric cars. But that's something that people would argue, right? That's a potential benefit of electric cars.
I'm curious as to whether or not you or anybody else has studied the effect of natural gas cars versus gasoline.
So really interesting question. Natural gas can be done off the shelf for $300 or $400 a vehicle, and nobody's doing it. And I don't know why. And a lot of us have natural gas infrastructure in our house. For $2,000 you can make a little thing that pumps the car full of gas. Really interesting question. It would be cleaner, I believe. It would be cleaner. But I don't think anyone's really done a study like this. We originally were going to, and then we sort of got away from it. But there's just no cars out there either. I mean, I think there's some fleets that use natural gas vehicles. But yeah, and it can be done, essentially overnight, right? The technology's there. And Honda was selling a filling station for a while, and they don't sell that anymore.
They had a Civic.
Yeah. I think you can still buy that. Within the last 5 years, you could have still bought that. I'm not sure if you can anymore.
One of the problems is it fills your tank up, your trunk up with the tank.
Right.
But anyway, and there's other things. It's not politically attractive either now, because methane is a super pollutant.
Right.
According to NRC. But to get back to your talk, there are 2 things that when you're looking at incremental harm, you're assuming that any pollution, even below the max, below the standard, is harmful. In other words, if you're in an area like North Carolina that's meeting all of its national ambient air quality standards, then presumably you make an argument that nobody's going to get hurt until you reach that.
Right. So
You're assuming this linear non-threshold.
So we are absolutely assuming a linear effect. But to be clear, what we're assuming, that linear effect, this is diving into the details of that model that I said Nick made up, is based on the background levels of pollution. Okay, so whatever the background levels of pollution are now, right, then what we're trying to measure based on the epidemiology is an increase in emissions. So it's not from a pollution-free environment, it's from the pollution environment that we have.
But the implication of the max is that there's a harm-free
That's right.
environment below the max.
Below that, right.
And
And we're not,
I'm
yeah.
just telling you that the model that
That's right.
now, and so that's.
Yeah, sure, fair enough.
So the other thing is that, did you use the fuel, the mile per gallon equivalent calculation that the EPA gives for the electric vehicles in calculating the?
So we didn't use the mile per gallon equivalent. We used the kilowatt hours per mile.
Right, but that kilowatt hour is the same thing. That is the amount of power that the car.
That's right. So there's,
consumes.
yeah,
Right. Well, what the EPA did that the DOE disagreed with is they never went, when they went back to the mile per gallon equivalent, get the 100 mile per gallon.
Right.
They assumed 100% efficiency from getting.
yeah, no. So,
Which is completely felonious.
right, that's right. So we use,
So you would have to take that same, whatever the amount used, you'd have to calculate how much power.
that's right, yeah. So what again, we're diving into the details, which is fine, it's good. The data that I showed you here includes losses from transmission, but not the local distribution. And so we're correcting that in the next version. We're going to account for the local distribution losses as well.
Account for the inefficiency of actually producing electricity.
Well, that's
No, that's not.
we're accounting for the losses,
Of the transmission.
but we're looking at the relationship between load is the electricity going into the grid and smoke and stuff coming out of the smokestacks, right? So that's the electricity going into the grid, the load.
Right.
So that accounts for any inefficiency, because we're looking at how much electricity gets put into the grid
Right, but
and
how
what's.
much carbon, for example, carbon fuel had to be used to produce that load.
No, we're not looking at that.
Well, and that's, and
that-
the EPA didn't either, and
yeah.
that's a factor of 3, so that would
Yeah.
change that.
We're not looking at because again, that's a very difficult calculation because you have to worry about the coal, right? You got to mine the coal. It takes carbon to do that. You got to, yeah. Well, there have been some studies that have tried to do that, right? And those studies have tended to show that the way it turns out depends critically on how you assume batteries are manufactured. In particular, where you assume batteries are manufactured. It's a very energy-intensive process. And so that can swing that life cycle calculation considerably, depending on the assumptions you make about that. But you're right, we do not include that in this. Right? We do include the inefficiency of making electricity in some sense. Yeah.
I had to go back to that benefit of reduced carbon dioxide question, but
Right.
In that social cost of
Carbon.
in that work, are they using the net benefit of reducing carbon dioxide globally, or just the United States?
No, so that's right. That is a global benefit.
So you're comparing harm in the United
States to, that's right.
benefit globally.
Right.
Why isn't that why isn't
So
that
we could
apples
try
to
to
apples comparison?
we could try to discount the carbon benefit and just say this is what happens in the United States. I mean, and that's
we
a
all know that global warming is supposed to affect and put country costs and
differential
benefits
place.
in
Yeah,
parts of the
sure.
world
And that's a
equally in even different parts of the United States.
oh, absolutely. And that's a fair criticism for a paper that's making a point about the difference in pollution from place to place, right? It's just that again, we're getting on fairly difficult turf to try to figure out what the benefits and costs are to various counties in the United States from a ton of carbon. That's, again, a calculation that would be fraught with
So for
uncertainty.
the United States, it's hard to know what way any of those numbers.
Yeah. I'm not going to disagree with that, right? Yeah, Jane.
Can you comment on whether a state like Colorado, which is subsidizing every car for $5,000, is that, or is the people of Colorado benefiting from that subsidy?
So I don't know the number for Colorado off the top of my head. It's in the green zone. It's probably about $1,500 benefit. So the idea is that they're benefiting $1,500 from air pollution. The subsidy is significantly more. It's like $5,000. So it's let me make sure I get that right. So I apologize. Those benefit numbers were for the lifetime of the car. That's right. And so you can compare directly to the subsidies. I may have said per year. When I Well, when I went to the graph of the 1974 cars, that was per year. But I do want to be careful. We want to make sure we compare lifetime. So the subsidy is a one-time payment. So you want to look at the lifetime benefit, and those numbers were lifetime benefits. Yeah.
My question is, did you account for when the cars are plugged in?
Yeah. So we did a number of different cases when we looked at that. Right. The EPRI, I forget what the acronym means, but it's an electricity group, has predictions about when they think cars are going to be plugged in. And we have data from power plant emissions for every hour of the day. So we can run a number of different scenarios. Say, let's assume they're plugged in mostly at night, right? Maybe a little bit during the day. Let's assume they're all plugged in on weekends. Let's make plugged in during summer months. I mean, we can do any kind of calculation that you like along those lines.
A large point, man, even if it's 5% in North Carolina, where our renewable energy is
That's right.
almost primarily solar,
It's not going to make any difference. That's right.
if people are commuting and then coming home and plugging.
That's right. Yeah, yeah. In fact, that time period when solar starts to go down and demand starts to go up, it's a real problem in the electricity industry, right? How do you manage that swing of electricity? We can do sort of a sensitivity analysis and see how those things matter. For this, we assume most of the charging is done at night, which is when a lot of people think charging is going to happen. Yeah.
So you said you did not consider disposal of batteries?
No, we didn't
But
consider.
do you suspect that it's significant?
Well, batteries are kind of a mixed bag because there might be some disposal costs, but they also might be used in grid storage and some other uses, so it's not completely clear what's going to happen to batteries. Eventually, they're going to die, right? But they might have some value in the interim period once they no longer power cars in other uses.
What are they're toxic in general? Or?
Well, they have a lot of heavy metals and things like that in there, right? Yeah, so it's going to be there will be a cost associated with recycling them. Although, like I said, there would be a benefit to having a used car battery. Will find a use before it actually finally dies.
Do you have anything to say to Volkswagen, who's spending $2 billion on electric vehicle infrastructure to make up for their NOx emissions?
So when I saw that, I didn't know whether to laugh or cry, right? So it's not clear that that's the best use of those funds. In the West, it would be a good use of the funds, maybe. In the East, not so good, but they're not making those kind of distinctions, right? So we actually wrote a quick paper on the NOx, because you can see from this model we have set up, we could evaluate exactly what happens. We knew where the cars were, we know where that emission goes, we know what the damages were, right? So our estimates are about $500 million worth of damages in the United States from those vehicles. That's just in the U.S. In Europe, people have done estimates. It's many billions of dollars, because there's a lot more diesels, of course, sold in Europe than in the United States. Yeah, great question. So we're going to try to do a bus paper, right? You think about diesel buses. You were asking about diesel buses in urban areas. There's probably some room for improvement with that. With anyone's been stuck behind a bus, right? And you can see that stuff coming out. That you think unless the grid is horribly dirty, and we're going to try to do that calculation, right? So buses use a tremendous amount of fuel, put out a tremendous amount of pollution. So we're working on buses. I don't know about trucks. We don't have anything in line to do trucks. And trucks are really dirty, too. So if you think about the numbers we quoted, on a per mile basis are 2 or 3 cents for a gas car worth of damages on a per mile basis, right? Trucks if a truck driven in an urban area can be like 75 cents per mile of damages. They're significantly dirtier. Yeah. And so one of Tesla's products is going to be a long distance truck, and you might imagine a world where those just drive around interstates and things like that, and you're losing a lot of that benefit because, again, there's not that much pollution that's being created in a rural interstate versus driving it in the city. But you're going to, it's harder to drive those cars in the city.
Any other questions or comments for Professor Yates?
Yeah, sure.
As states wrestle with transportation costs and how to pay for the infrastructure, such as North Carolina did Florence and all
Right.
that damage, and more states are considering modeling mile
Right.
GPS.
That's right.
Do you think they will incorporate?
I think that's an appealing system in a number of ways, right? If you think about to the extent that we can calculate the damages that you cause to other people when you drive your car, it might be nice to make people accountable for that, right? To the extent that we can do that, and a per mile charge is one way you can do that. In addition to congestion and accident externalities and other things like that, yeah, I think that's an improvement, right?
So you'll become famous with this study?
No. Luckily, I will never become famous for anything. So.
Professor, could folks access your paper, your study?
Yeah, so it's probably behind a paywall, but if they want it, I can send it to you.